Okay, this is Station Lab with the Phet Lab. I logged in and I set it up just like the direction shows you, and just kind of set up and paused it at three different areas. When I did so, I chose an area where the spring was down, and it was kind of at its amplitude, so the acceleration was pointed back towards equilibrium, but at this point there was no real velocity going on at this particular point. And then just kind of let it play and then pause it. I wanted to try to do areas that weren't identical to each other. And that dashed line was, I think that was the equilibrium that they were representing in the diagram. They may have called it something a little bit differently. But I chose another one that was right here where my acceleration was still up, but not by as much. And the velocity at this point was going down. And then for the third one, there's my equilibrium line. Stop this one up above equilibrium. So my acceleration should be down. And at this point, my velocity was up, so it was on the way up. Using a stopwatch, we want to, and on the slow feature, we wanted to figure out what the period was. And for me, it was 0.85 seconds based on the information or the parameters that I had set. So I increased the weight. How long does it take for the spring of one oscillation? So I changed the mass from 100 grams to 150 grams. Has the spring's period increased, decreased, or stayed the same? Well, increasing the mass, what is that going to do to the period of a spring? Well, the period of a spring is 2 pi times the square root of m over k. What do we anticipate happening if m gets bigger? Well, the m is in the top of the fraction, but it's being square rooted. So for me, it went up to 1.08. So if I increase the mass, I should get an increase of the square root of that number as a factor. So yes, it did. The period did increase. And then it says, provide an explanation. Well, my explanation is going to be based on the formula. 2 pi times the square root of m over k is the period of a spring. So if you increase the mass, you're going to increase the period. Increase the spring constant, top of the screen. It didn't call it spring constant. It called it like strength of spring or something like that. And time how long it takes for the spring to complete one oscillation. So I increased it, and now my period is 0.9. So I'm increasing the spring constant, which is the denominator of my fraction in that formula, 2 pi times the square root of m over k. So if I increase the spring constant, that's going to decrease the period based on that formula in the relationship. What happened to the amplitude of the oscillation in 3 and 4? Or let's say going from 3 to 4. Did it increase or decrease in each situation? Or going from situation 3 to situation 4? So to make sure, I kind of reduced the spring constant pretty low, and then I increased the spring constant because I like to see it exaggerated, and it helps me see what the differences truly are. So my amplitude decreased as the spring strength or spring constant increased. I saw a decrease in the amplitude. Now we're doing pendulums, and I first had my pendulum deflected to the left side, and I had to draw the velocity and the acceleration. Here I actually mislabeled this. You see that I labeled velocity, that should have been acceleration. I mixed up the colors on the legend of which one was which. So that's actually acceleration pointed back to the right, not velocity. I apologize for that. So for anybody listening, they know the problem. Anybody just watching this without the sound is going to wonder why I got that wrong. So anyway, when it's at equilibrium, now it's showing the acceleration pointed straight up. That's because there is no tangential acceleration. There's only centripetal acceleration at this point. So the acceleration is up while the velocity is to the right. And then when we were on the far right side, we had the velocity then going back to the right just a little bit, so it's a tiny bit still going to the right. It was slowing down to a stop, and the acceleration pointed back towards the left, which is back towards the equilibrium. And again, the acceleration they're showing us is a combination of the tangential and the centripetal. At amplitude, there is no centripetal because there's no velocity. And then at equilibrium, it's all centripetal. Describe how the direction of acceleration changes as the bob swings. Well, the velocity points in the direction of motion. The acceleration is a combination of the tangential and the centripetal. Tangential comes from the restoring force. We know the restoring force is 0 at equilibrium, it's maximum at amplitude. But the centripetal is v squared over r, maximum velocity at equilibrium, so you'd have maximal centripetal, that acceleration that keeps you moving in a circle. In the option bar on the right, change the mass of the bob, okay, and did the period of the motion change? What's our formula? 2 pi times the square root of L over G? Yeah, changing the mass here is not going to change anything. Look at the formula. Mass doesn't matter when it comes to a pendulum. Did the amplitude change? Well, we said the period didn't change. What happened with the amplitude? Let's take a look at that. Let's try it out on a Phet and then just see. For me, the amplitude did not change. Mass does not matter when it comes to a pendulum. In the option bar on the right, change the length of the string. Did the period of motion change? Did the amplitude change? Explain what you observed. The length of the string for a pendulum is in the formula 2 pi. The period is 2 pi times the square root of L over G. A longer string would result in a longer period because L, the length, is in the numerator of that equation that's in the radical that you have to square root. So a longer string will result in a longer period. For me, when I extended the length of the string, I actually saw a shorter or smaller amplitude. It did not go as far out. So I had a longer string and it didn't go nearly as far as deflection, the degrees that was deflected from the equilibrium. In the option bar on the right, change the acceleration of gravity. Did the period of motion change? Did the amplitude change? If I increased the gravity, I got a shorter period because gravity is the denominators, which you're dividing by. So now you're dividing by a smaller number. Actually, I made gravity 0, and I went out of simple harmonic motion. It just spun all the way around, right? So nothing was restoring it back to any equilibrium. But then again, you got to play with the parameters, go to each extreme end, and just kind of learn what they do. Subtle changes are going to be too hard to see what the subtle difference is. When I decreased the gravity, it increased the amplitude because the restoring force was less, so it went further out before it was pulled back. And then in the option bar, there's an option to change the friction. What friction is most likely to be referring to? So the friction is air resistance. And what happens when you increase the friction and why? Well, you end up losing energy. Friction is a non-conservative force. You're losing energy, and eventually your pendulum just comes to rest.